Today we want to talk about maximal inequalities, which means that we want to bound expectations of random variables we cannot exactly compute by a certain term. And today we want to bound the expectation of the maximum of finitely many random variables that share a certain characteristics, namely the cumulative generating function can be bound by the CGF of a normal distribution. So to start, we define the cumulant of a random variable x, which is given by the natural logarithm of the expectation of the exponential of s times x. In the case of a normal distribution, a central normal distribution with variance sigma squared, it turns out that the CGF is given by s squared times sigma squared over 2. What we now want to show is that if we have random variables that are sub-Gaussian, which means that their CGF is less than the CGF of a normal distribution with variance sigma squared, or in this case nu, then we have that we can bound the expectation of the maximum of all these xi's by the square root of 2 times the logarithm of n times nu, so the proxy variable for the variance. So proof: we take an arbitrary s greater 0, and we note that the function that maps x to the exponential of s times x is convex, so we can apply Jensen's inequality. So this is Jensen's inequality. So when you compare a convex function with a straight line, then the convex function will always be below the straight line when you fix 2 points. And this is the reason why somehow this term here, which is f of something, which must lie on this curve, is less than the expectation of f of x. So the expectation of f of x could be seen as these 2 points and then the average, which lies somewhere here. This is a rough explanation why Jensen's inequality holds. So we want to apply this to the exponential of s times x. So we bound this from above by the expectation of the exponential of s times the maximum of the xi's. The exponential of the maximum is the same as the maximum of the according exponentials. And now we can upper bound the maximum by just the sum and pull the sum outside the expectation. And now we can use the assumption that all the CGFs of our random variables are bounded by s squared times nu over 2. So this gives us the sum of the upper bounds. So here are the upper bounds. So the question now is, how do we select s in order to get this expression as small as possible? Because what we've done until now is that we have bounded this expression by this one, and when we take logarithms on both sides, it gives us this right here, and this already looks like what we're going for. The only thing is that we have to choose s in a way such that when we pull s on the other side, then the expression on the right hand side is as low as possible. So this could be achieved by just defining a function and then computing the optimal value, hence the minimum. So we define this function f of s, which looks somehow like this. So we have a linear term, s times nu over 2, which is when s is very large, this term disappears. So it is just a straight line. But when s is very small, then this one disappears and this one gets very large. So we almost have a 1 over x situation, which goes like this, and we get this convex shape. So we just have to compute the derivative and set it to 0, and then we see that the optimal s is just this term here over the times the reciprocal of this term and the square root of that. And when we plug it into f, then we'll see that we'll just get the desired result. If we look at the xi's being normal distributed, standard normal distributed, then we have the result that the limit of the ratio of the bound and the expectation is equal to 1. So asymptotically, the expectation of the maximum of standard normal random variables approaches the square root of 2 times the logarithm of n.